In this video series, we're looking at the general linear model, and we have been working our way through various designs so that we could look at the model for each of the designs. In this video, we're going to look at two designs, the randomized block design and the repeated measures design. Why are we looking at two of them within this same video? Well, take a look. Here is the randomized block design. Here is the repeated measures design. Keep your eye on the linear model at the bottom. I'm going to switch back. Nothing happened. Those two designs have the same model. Let's go ahead and start with the repeated measures design. Subjects are measured J times. The effective time or interventions applied between measurements can be assessed. Each score is the sum of the mean, the subject effect, the effective time, and the residual that is unaccounted for by experimental factors. So Y here is the observed score. Mu is the mean of all the scores. Pi is the effect of the particular participant. And we're able to actually measure and weed out that effect because we're measuring each participant multiple times. So if you average across all the times and look at the differences among participants, that's a participant effect. Now, we're not going to be able to inferentially analyze that effect, but we don't need to. We don't care to. We're just wanting to take that effect out so that we can analyze alpha, that is the effective time. We want to look at that effective time, and by taking out between subjects out of the residual, we get a smaller residual and can analyze the alpha effect with more power. So we have a score equals the sum of the mean, the participant, the effective time, and note here that there's going to be a separate effect for each time, so J is going to vary across the number of times you're taking measurements. So at time 1, the little j will be 1, at time 2 it will be 2, and for each of those times we're going to have an effect of being in that time. And then we have the epsilon or residual for person I at time j. So for this particular one, when I did this in a previous video, we were looking at soccer players and they were sprinting through an obstacle course as fast as they can. And you can see here from the box plot that we had 6 different trials for those soccer players. So when I come down and look at the factors down in the ANOVA table, we notice that we don't have an interaction even though we have 2 factors. The reason that is because one of the factors is between subjects, and we're actually pulling that out of the residual that we're going to use to test the trial times. So we're pulling this out and not testing it as a factor, but taking it out of the residual to make this residual down here for the within subjects factor to make it smaller. So note we have a between subjects factor, and I don't even have to worry about the inferential conditions. I don't need to meet those conditions here. Why? Because I'm not even going to do anything with that. It's just a residual. It's not a factor that I'm actually going to test. But it's like having a separate ANOVA table up here that we're not going to look at because we don't have any particular factor, we only have residual. And then another ANOVA table down here we are going to look at, and that is the ANOVA table for the within subjects factor. So trial is a within subjects factor. Why? Because every soccer player is going to be in every trial. So the trials are correlated. And then we have a residual for that. So here is the pi, which is actually a residual taken out of the main residual. Here is our alpha, and then here is our epsilon, which is left over. And of course, the only other term in the model is mu, which is the mean across all soccer players. So looking at my principles for valid inference, I only need to worry about within subjects. And sphericity here is going to involve looking for through all the pairs of differences. So even though we have up here 6 different trials that we're looking at, here are the 6 different trials, we're actually dealing with 15 pairs among all possible variations of the pairs of trials, trial 2 to 1, trial 3 to 1, trial 3 to 2, and so forth. And so sphericity has to do with homogeneity of variance among those pairs of differences that we're looking at here. Then we look at the residual here and look for normality for the within subjects factor. That's the only thing we need to do, the only one we need to look at here. We're not looking at interaction because we can't have any. We don't have any interaction because remember, this factor here is only being used as a residual, not as an actual factor. So we look at the omnibus test here, which is this one for trials. We find that there is a difference among trials, that the speed, you can see it here in this line graph, that the speed differences that we have can be seen changing from trial to trial to trial. And in fact, we can make inferences assuming we've met the condition for valid inference. That would lead me then to look at pairwise confidence intervals. This is a main effect of trial, a main effect. We don't have an interaction to look at. And since I was able to reject, then I can look at post hoc pairwise, and I use Tukey by looking at all pairwise. But if I looked at fewer than all pairwise, I could use Bonferroni, or if I was going to actually look at the data itself to decide which confidence intervals I want to construct, then I would use Chaffee, because Chaffee is a fishing expedition confidence interval technique in which you can actually look at the data and still maintain your type 1 error rate. For the others, for Tukey, you're either doing all pairwise, and for Bonferroni, you need to plan in advance. So that's the repeated measures design. What about the randomized block design? What is different? Well, if instead of having each of these soccer players do each of the 6 trials, we had instead, say, tested the speed of the soccer players, maybe had them all run the 100-yard dash and then taken the fastest one and matched the 6 fastest ones together and put one of them in an obstacle course, then another, and then another, and then another, then we would be blocking. And in that particular case, each participant would be in only one trial and only one trial, each participant in one and only one trial, but we would have a block because we would have correlation among the trials because we matched up the soccer players based upon an extraneous variable. Now, that would not make a lot of sense in this study because we actually wanted to see the effect of time. We wanted to see if they fatigued or if they got better with practice. But it does make a lot of sense if you're encountering the possibility of multiple treatment interference. Like if you want to look at the same participant across 3 different educational interventions, you can't erase their memories when you put them in the second intervention. You can't erase the memory from the first. That's multiple treatment interference. So what could you do? You can't do repeated measures. But if you want to use this kind of design and take advantage of the fact that you're able to reduce the residual, you could do so by blocking on an extraneous variable, looking at something like prior academic achievement and matching participants up on that prior academic achievement into blocks. And then that pi becomes a effect in the study that is treated as a residual. It reduces the actual residual, allowing us to look at the difference between conditions with more power. So subjects are first matched into blocks and then randomized to J different experimental conditions. Each score is the sum of the mean, the block effect, the effect of the experimental condition, and the residual that is unaccounted for by experimental factors. Whereas with the repeated measures design, exact same model, but subjects are measured J times. The effect of time or interventions applied between measurements can be assessed. Each score is the sum of the mean, the subject effect, the effect of time, and the residual that is unaccounted for by experimental factors. So that's the randomized block and the repeated measures design. And in the next video, we'll look at combining both between and within subjects design. These two designs, we only focused on within subjects. We removed the between subjects effect. But in the next design that we'll look at, we're actually going to have factors that we can test for both between and within subjects.